So in class, we went through the 5 basic steps for a hypothesis test, right? And I even gave you a summary sheet with what those 5 steps were, all right? And that's what I've got outlined here because I know I'm going to use those for every hypothesis test. Now, we also talked about the fact that just like with confidence intervals, if you have a situation where you do not know sigma, you do not know the population standard deviation, then you have to switch and use T instead of Z. That's literally going to be the only change in the hypothesis test that you see in 9.3, right, is how we find our critical value. All right, so I wanted to go ahead and work through this example with you so that you could see it before next week. And this is in your notes for section 9.3. All right, so first thing we're going to do, read through our problem, write down all of our information, and label our null hypothesis and our alternate hypothesis. Okay, both of these are going to involve statements about the mean, mu, and we know the null hypothesis is going to have equality. All right, so a software vendor claims that a new version of their operating system will crash less than 6 times per year on average. All right, so there's our statement about the mean. It's stating that it's less than 6, so that's going to be my alternate, and we know the null hypothesis is always just going to be equal to that same value. All right, now if we continue reading through here, we have a sample data set. Sample size is 41, so there's my N. The sample mean, which is a value of X bar, is 7.1. And then notice our standard deviation here. This is only for the sample. It's not for the whole population. That means it is a value of S, not sigma. And because we do not know sigma, that lets us know we're going to need to use T. Okay, just like we did for our confidence intervals. All right, now, when I go to find my critical region, right, we always sketch it out. Even though Alex doesn't have you actually enter that sketch it out because it makes your decision much easier. Now, when you sketch the curve for T, just do a basic bell-shaped curve like you did for Z. It's technically a little bit wider, but that doesn't matter. You just need to make yourself a basic sketch. All right, now, to shade my critical region, I need to look back up here at the alternate hypothesis. And because it contains less than, I know this is going to be a left-tailed test. Now, 2 things that I can gather from that, right? One is that my rejection region will be in the left tail of the curve, right? That's that rejection region or critical region. The other thing that I can gather here is that my critical value will be negative because for a left-tailed test, you're below 0. All right, now because this is a T that we're looking at here, we're going to go to our T table. All right, and remember, you can access these in ALEKS by clicking on that button with the bar chart. Now, when you use the T table, you are going to be asked for a new value here, something called degrees of freedom. And for this test, that's always going to be N minus 1. And then these values across the top here, these are your values of alpha, okay, that level of significance. So let's come back over here. We're going to need degrees of freedom, and we're going to need level of significance. All right, so our sample size was 41. We're just going to subtract 1 from that to get 40 degrees of freedom. And then we were told to run this test with a 0.05 level of significance alpha. Okay, that's what I'm going to take to my T table. So 40 degrees of freedom all the way down here at the bottom. And we want alpha at 0.05. All right, so if I follow this all the way down to 40 degrees of freedom, sorry, it's a little bit cut off there, but the value that I'm seeing is 1.684. Now, the thing about your T table, it only gives positive values because it's a symmetric curve. So this is where it's important that as soon as you saw it was left-tailed, you understood that this critical value needed to be made negative. If it was a right tail test, that would not be the case. All right. Now, just like we did for Z, the next thing we're going to do is compute our test statistic. The formula looks a little bit different just because of notation. We're using S, the sample standard deviation, instead of sigma, but it's the same calculation that we did for Z. All right, so my sample mean, X bar, is 7.1. Mu that I'm testing here is 6. Standard deviation S is 3.6. And I'm going to divide that by the square root of my sample size. Notice this is n, not n minus 1. Okay, you only do n minus 1 for degrees of freedom. All right, now t-values, like they are in the table, are usually rounded to 3 decimal places. And so I would state my test statistic here at 1.957. All right, now remember how you make your decision. If that number is in the critical region, you reject the null. If it's not in the critical region, you fail to reject or do not reject the null. This one quite obviously is not in the critical region, right? It's nowhere near it because this is actually a positive number. So our test statistic is up here. All right, but again, what's important is that our test statistic is not in the critical region. And therefore, we do not reject the null hypothesis. All right, and then we know how we interpret that information, how we state our conclusion. If we're able to reject, then we can conclude what's in the alternate. If we're not, like we aren't here, then we have to say there is not enough evidence to conclude what's in our alternate, which said that the mean is less than 6. Okay, so again, what I want you to see here, just like we talked about with the confidence intervals, right? You just have a choice between using Z and using T. If you know sigma, the population standard deviation, you use Z. If you don't know sigma, right, if all you have is a sample standard deviation, then you use T. All that changes is the way you find your critical value. Everything else is done the same way for every hypothesis test.